Yeah, greetings to all. In the last class we have discussed about the basic principles of magnetic fields and magnetic field sources, Faraday's law, Ampere's law, Fleming's left hand and right hand rules, thumb's rule, all those things we have discussed, right. So, in this class we will discuss about the magnetic materials. So, what kind of magnetic materials we will utilize it for designing the magnetic circuits or our electrical motors. Okay. And also we will discuss about the BH curves. Okay. So, if we will see the periodic table of elements, there are 118 elements are exist as of now. Okay. So, this periodic table of elements, okay, all are exhibits the magnetic properties, okay, whether it may be diamagnetic material or whether it is paramagnetic, whether it is ferromagnetic or antiferromagnetic. Okay. So, from this periodic table we can observe that all blue color one represents the diamagnetic materials and green color one represents the paramagnetic materials, and red color we can see here few elements, that elements exhibits the ferromagnetic materials, and few other materials at different temperatures will exhibit different type of magnetic properties. Okay. Now, we will see how these materials will behave and what kind of materials from this 118 elements we will select for designing of magnetic circuits. So, first I will discuss about the magnetic material, not only the diamagnetic, any type of material we will discuss with respect to the basic terms magnetic domain, magnetic dipole and magnetic susceptibility. So, these three terms I will utilize it for explaining the different types of magnetic materials. Okay. So, if we will consider the magnetic material here showing, okay, this material is a combination of huge number of atoms. Okay. Let us consider a set of atoms whose magnetic material magnetic fields are aligned in one particular direction. That group of atoms we can call it as a magnetic domain. Okay. The definition if we will see, it is a region within the magnetic material in which the magnetization is in a uniform direction. Okay. And magnetic dipole, it is a small or tiny magnet. Okay. It is a combination of few magnetic domains, but if we will talk about the magnetic material, it consists of huge number of magnetic domains. Okay. Now, magnetic susceptibility, the magnetic susceptibility is a measure with respect to the this particular magnetic material. Let us assume that we are applying a magnetic field from this direction. Okay. How much this magnetic material is magnetized. So, how to measure that thing? That quantity is nothing but magnetic susceptibility. Okay. It gives a measure how much a material will become magnetized, and it is a ratio of magnetization and magnetic field intensity. Now, we will discuss about the different type of magnetic materials. So, first I will start with diamagnetic materials. We can see the different type of diamagnetic materials as per the periodic table at right hand side has shown. Let us consider the diamagnetic material. If we will place in a magnetic field, or let us apply a magnetic field to this diamagnetic material, the induced fields in this magnetic material, okay, are exactly opposite direction to the applied magnetic field. Because of this reason, this magnetic diamagnetic materials will repels the applied magnetic fields, and there is no movement in magnetic domains. Okay. And magnetic susceptibility is negative and it is very small value. and the susceptibility will not depends upon the temperature. And if we will see the relative permeability of the material is less than 1. In the last lecture we have discussed about the Ampere's law, right. If the mu r value is very small or negligible, then there is no use of it, right. If we can, even though if we are utilizing the core, we are not at all increasing the magnetic flux density. Okay. So, these materials will not enhance the magnetic fields. Okay. And the examples for these diamagnetic materials are copper, silver, gold, zinc, silicon, bismuth, mercury, nitrogen and etc. Okay. We can see from this periodic table all elements exhibits the diamagnetic materials. Next we will discuss about the paramagnetic materials. Here also if we will place the paramagnetic material in a magnetic field, the induced magnetic field magnitude is very small, okay, and the direction is in the same as the applied magnetic field, but the magnitudes are very small. Okay. The magnetic domains are still randomly oriented because of the lesser magnitude of induced magnetic field, and the susceptibility value is positive but very small, almost negligible. Okay. For diamagnetic materials it is negative but small value, for paramagnetic positive and small value, there is no use of it. If we will utilize the core with respect to the paramagnetic materials, we cannot enhance the permanent or flux density. The relative permeability of the paramagnetic materials also we will see here, it is very less, even though it is greater than the permeability of the free space, but the value is very less. And the examples for the ferromagnetic materials are lithium, sodium, magnesium, potassium, calcium and all other elements which are green colored and highlighted in the periodic table, we can see at the right side corner. Okay. So, all this material exhibits the paramagnetic material properties. Now, we will see the ferromagnetic materials. Similarly, here also if we will apply a magnetic field, okay, we can see in this figure, if there is no magnetic field, all domains are randomly oriented. If we will apply a magnetic field B to this particular type of magnetic material, all magnetic domains are aligned in one direction and induced magnetic fields also in the same direction of applied magnetic field. The simplest example I can give how ferromagnetic materials will behave, like consider a magnet, either it is a permanent magnet or electromagnet. Here I am showing with the electromagnet, and take the simple iron piece. If we will bring the iron piece into the magnetic field, the all magnetic domains of iron are aligned in one direction and it will be attracted by the magnet. That is what we can see in this figure. All domains are directed or oriented towards the applied magnetic field, but the pole formation with respect to the iron piece and with respect to the source side are opposite. Here north is there and here south is there. Because of the attraction, opposite poles will induce in the iron piece. The susceptibility value is large and positive, okay, and it will depends upon the temperature. If the temperature varies, susceptibility value also will vary. I am not giving the exact equation for the susceptibility, but it depends upon the temperature. The relative permeability value is very high. We can see the relative permeability for different materials like iron, cobalt, nickel. Like for iron it is 5000, for cobalt 250, for nickel 600. For cobalt iron, like alloys I am discussing with respect to the three materials, their respective alloys. Cobalt iron, iron with pure form 99.95%, 2 lakhs relative permeability, and silicon plus iron, steels. We are utilizing steels in everywhere, right, in all magnetic circuits. So, that permeability is 4000. The relative permeability is the unitless quantity, because the mu value has the units and mu naught value also units, and relative permeability does not have any units. The examples for the ferromagnetic materials are these things only: iron, cobalt, nickel and their alloys. Antiferromagnetic materials. When there is no magnetic field, all domains are unaligned, are oriented in different directions. If we will apply a magnetic field, there is a induced magnetic field in the same direction of applied magnetic field, but the magnetic domains are aligned in anti-parallel manner with respect to the neighboring magnetic domain. Okay. The induced magnetic field magnitude is less or very less. So, susceptibility value is small and positive, and mu r value is greater than 0, but almost negligible. Okay. The examples for this type of magnetic materials are manganese, chromium and many of their compounds like manganese oxide, manganese sulphide, chromium oxide and nickel oxide, etc. And ferri-magnetic materials, this is the last type. Here the magnetic domains are aligned exactly opposite and parallel to each other. So, here one line is in the same direction of applied magnetic field, and other line or other fields are exactly opposite to the applied magnetic field. Similarly, other things. So, the magnetic domains are aligned with the induced or applied magnetic fields, but opposite and parallel in nature. Okay. Because of the different magnitudes of these domains, parallel domains, there is a resultant magnetic field. The susceptibility value is large and positive. The relative permeability value also higher as compared to the antiferromagnetic materials, but slightly lesser as compared to the ferromagnetic materials. The examples are all ferrites like ferrous ferrite and nickel ferrite, etc. From this analysis, we have seen that ferromagnetic materials and ferri-magnetic materials are giving higher permeability values and higher susceptibility values. Along with that, these materials are easy to magnetize as well as demagnetize. Because of these properties, for designing the magnetic circuits, we will utilize only ferromagnetic materials as well as ferri-magnetic materials. Can we use the iron, cobalt, nickel, ferromagnetic materials directly, or we have to utilize the alloys? Depends upon the application and depends upon the type of equipment. We can utilize the iron, cobalt, nickel directly also, pure form, but the cost may be higher, and alloys will give the better performance with respect to the pure materials. I will consider a simple example of pure iron. So, what are the characteristics of the pure iron? We will see here. It is soft and rust can happen or corrosion will happen, and it is easy to melt, malleable, lower resistivity. Because of the lower resistivity, higher eddy current losses may happen in the pure iron material. So, in order to enhance these properties, we can add the iron plus some other materials, okay, silicon, carbon, manganese, etc. Alloy is nothing but a combination of different materials. Okay. The properties of alloys, we can attain whatever the property we want. Let us assume that we want the hard material. So, pure iron is soft, but if we want the hard, then we have to add some other element to iron. So, hard, rust free, higher strength, lower weight and lesser losses because of the higher resistivity This higher resistivity is attained because of the addition of other element to the iron, and at the end cost, design complexity and lifetime we have to check. Okay. Generally used iron alloys are in the magnetic systems, we will see now carbon steel, where iron plus carbon we are utilizing. The applications we can see here: construct the buildings, bridges, pipes, fittings, etc. Similarly, alloy steel, iron plus carbon plus aluminum and other materials. Depends upon the application and depends upon what is the property we require. Based upon that, we will mix the composition of different materials. And stainless steels, for example 18 and 8 steel, here some typo mistake is there. So, it is just 18 and 8, okay. 18% of chromium and 8% of nickel, we will utilize it for designing 8 steel. And applications we can see medical, kitchen, mission bearings and etc. Similarly, cast iron, where iron plus carbon plus steel and other materials are utilized for designing this carbon cast iron alloy. What are the magnetic materials used in the electrical machines? We can find in this IEEE papers, IEEE paper by Andreas Krings. Okay. So, different magnetic materials we can find in this table: cobalt iron, nickel iron, with respect to different material composition here, 49% cobalt and 49% iron and 2% of others, we will utilize it in the cobalt iron. Similarly, other materials like some non-oriented SiFe, silicon steel, where 1 to 3% of silicon and iron is the remaining portion. Okay. The flux density values we can see here. Okay. For cobalt iron 2.1 Tesla, for SiFe steel it is 1.15, and material densities also we can see. More details we can find in this IEEE paper. These are the materials generally we will utilize it in the electrical machines. Now, we will discuss about the BH curves. Okay. When there is no magnetic field, okay, let us consider the magnetic material, and if we are not applying any magnetic field to that particular material, then all domains are randomly oriented. If we will apply a magnetic field, B equals to not 0 and finite value we are applying, then during that particular condition, the all magnetic domains are aligned in one particular direction with respect to the applied magnetic field. Example also we have discussed with respect to the ferromagnetic material. Now, the question is, if we will remove this applied magnetic field, okay, maybe I am pointing out with the laser pointer, if we will remove this applied magnetic field, can we retain the same phenomena with respect to case 1? All domains will be randomly oriented? The answer is no, because of the magnetic fields that are applied at the previous stage and magnetic properties of the magnetic domains. So, if we will remove the magnetic field also, still some domains are aligned in the direction of applied magnetic field in the previous state. This is called as a magnetic memory or residual flux or retentivity, different names we can call it. So, in order to bring to its original state, okay, where the magnetic domains are randomly oriented, in order to bring this situation, we have to reverse the magnetic fields. So, if we will reverse the magnetic field, here at the left side corner case 4 we can see where the magnetic fields are reversed. If we will reverse the magnetic fields, we can attain the case 1, not exactly, but all magnetic domains are randomly oriented. Okay. So, if we will change the magnetic field like initially 0, then one direction, and then we are reversing the direction of magnetic field. So, if we will vary the magnetic field in a AC manner, okay, alternating manner, then we can see a loop formed by the magnetization curves. Okay. That loop is called as a hysteresis. We will see in detail about the hysteresis loop in the coming slides. So, if we will vary the magnetic field in a AC manner, then we can see a hysteresis loop. Before going to the BH curves hysteresis loop, we will discuss the basic principles. The magnetic Ohm's law, where flux is equals to magnetomotive force and divided by reluctance. It is the analogy with respect to the electrical circuits V by I, and flux equals to B into A. The flux lines are B fields in a particular area, and Ampere's law gives the relation between the MMF and magnetic fields created by the current. Okay. So, from these two equations we can see that flux is directly relation to the current, and V is in directly proportional to the current, and H also is in the direct relation with the current. In electrical circuits, if we will consider the linear characteristics of Vi, generally the resistance will not change. If the temperature is varying, then we may not see the linear characteristics. So, assume that here the resistance is not varying, then linear characteristics we will see. So, similarly for magnetic circuits also, flux versus MMF or B versus H, we will see the linear characteristics, that is 1 by reluctance. Here also 1 by resistance, IV characteristics. 1 by reluctance is nothing but permeability. Okay. If the magnetic circuit is ideal, and if we are assuming it as a linear circuit, then there is no saturation and reluctance is assumed as a constant value. But most of the magnetic circuits with respect to the practical applications which will not gives the linear characteristics. Okay. So, we will see the nonlinear characteristics between the flux versus MMF or B versus H. So, here we can see that red color line is the saturation. Even though if we will increase the current or if we will increase the MMF, there is no change in B value. Okay. If we will increase the current, H will change, but B will not change, because at this point already all magnetic domains are aligned in one particular direction. Okay. The magnetic material will be saturated, and the permeability during the saturation condition is 0. Now, we will discuss about the exact BH curve or hysteresis loop. Consider a point at the origin, okay, where the magnetic domains of a material are randomly aligned. Okay. Here current equals to 0 with respect to the excitation circuit, and B fields as well as H fields equals to 0. Okay. If we will increase the current or if we will increase the MMF, so B fields will be increased and the magnetic domains will be aligned with respect to the applied magnetic fields. The magnetic fields are applied in this direction in a positive manner. So, few domains which are blue colored in this figure are aligned with respect to the applied magnetic field because of the lesser MMF and lesser B fields. We can see here a line with respect to the B and H curve, then we can observe that the magnitude of applied B field is less. Because of this thing, the less magnetization is happened here. If we will increase the current and if we will increase the MMF as well as B fields, then all domains will align in one particular direction. We can see here in this plot at point C, where current, B fields and H fields are reached to the maximum. Okay. If we will increase further the current or MMF, okay, what it will happen? If we will increase the current or MMF further with respect to the point D, there is no change in magnetization, okay, because all magnetic domains are aligned in one particular direction, that is with respect to the applied magnetic fields. If any change in H or any change in current, there is no change in B fields, that means core is saturated. Here permeability is equals to 0. If we will take the slope with respect to this line, okay, slope is 0, it is parallel to x axis. Now if we want to bring back the magnetic material to its original state, what we can do is we will remove the applied magnetic field. Once if we will remove the applied magnetic field, okay, current will become 0 and MMF becomes 0, but the magnetic domains still in the direction of applied magnetic field in the earlier state, that is D, okay, or C. So we will see some magnetization in the material, or we can call it, this state it as a memory, magnetic memory or retentivity or remanence. The definition for retentivity is, it is a measure of magnetization left in the electromagnetic material after an external magnetic field is removed. The units are Weber per meter square or Tesla, same as the B fields. And if we want to bring back the material to its original state of A, like where the all magnetic domains are randomly oriented, we have to apply the negative or opposite direction of B fields. So from point E to F, in order to attain the characteristics, we are reversing the applied magnetic field. Now we are reversing in this direction, okay, right to left and here left to right. At the point F, the B fields equals to 0, but H is not equals to 0. This is called it as a coercivity. The coercivity definition is, it is a measure of ability of a ferromagnetic material to withstand external magnetic field without the becoming demagnetized, okay, or simply we can say that the material reached to its original state where the magnetic domains are randomly oriented, B fields equals to 0, but H is not equals to 0, magnetic field or intensity or MMF is there. Now from F to E, still F to G, still we are applying a magnetic fields in a opposite direction or current in a opposite direction. Then the material will reach to its maximum state where the magnetic domains are aligned in a reverse direction with respect to the applied magnetic field. We are applying a magnetic field in this direction, right. So all domains are arranged or oriented in the same direction. Similarly it will be same, if we will apply, if we will increase the B fields further or MMF further, then it will go into the saturation where there is no permeability, permeability is equals to 0 and there is no change in B value, but the change in H may happen if we will increase the current. So similarly retentivity we will see at the current I point, at I point we will see the retentivity again or magnetic memory, and then if we will from the point I, in order to bring the material to its original state, that is J, so we have to reverse the magnetic fields again. At point I we are reversing the magnetic fields direction. So then the magnetic material will retain its original state where all magnetic domains are in random direction. So if we want to magnetize the material again, then we have to increase the B fields as well as H fields, then it will reach again to the point C. So if we will see the BH loop for an alternating quantity, we can see with the blue color dot point, which is varying with respect to the from point J, C, E, F, G, I and J. So, that loop we can see, that is the actual BH loop for a material if the alternating type of B fields are there. Next, for soft magnetic materials and hard magnetic materials, how the BH curves looks like we can see in this slide. For hard magnetic material, wider BH loops we can observe. For soft magnetic materials, narrow BH loops we can see. So, the area under the curve, BH curve, is represents the hysteresis loss, the energy dissipation or energy loss happening in every cycle we can say. Okay. The maximum flux densities or saturated flux densities we can see in this table, where ferrite has saturation flux density 0.3. Generally we will utilize the ferrites for high frequency applications. SI steel and powdered iron, amorphous glass and Mu metal, all these materials we can utilize it for designing the magnetic circuits. Generally SI steels we will utilize it for designing the electrical machines. 1.2 for CRGO steel and 1 for CR NGO steel, depends upon the composition, this value may be higher. Here CRGO is nothing but cold rolled grain oriented steel. Generally we will utilize it, this type of material in transformers, where the magnetic domain properties are aligned in one particular direction, whereas in CNRGO, cold rolled non grain oriented, the magnetic domains or magnetic properties are aligned in all directions. We will utilize it CNRGO steel in electrical machines and generators. So, we will see the examples of soft magnetic materials and hard magnetic materials. Here examples: iron, cobalt, nickel and their alloys, all ferromagnetic materials will exhibit the narrow BH curve, comes under soft magnetic materials. Hard magnetic materials are used in designing of permanent magnets, or permanent magnets by default has the wider BH loops. The examples: samarium cobalts, alnico and neodynamic magnets and strontium ferrites, all these materials consist of wider BH loops. So, with this I am concluding this class. In this class we have discussed about the different type of magnetic materials, which type of magnetic materials we will utilize it for designing the magnetic circuits, and also we have seen that how BH curves looks like. Okay. Thank you.